Dámy a pánové, já vás velmi srdečně vítám na Pražském hradě, a to konkrétně v Nejvyšším purkrabství, na další z naší sérii přednášek Věda na hradě, kterou organizuje Správa Pražského hradu společně s Ústavem organické chemie a biochemie a Karlovou univerzitou. A také moc děkujeme za podporu nadačnímu fondu IOCB Tech, který vlastně tyto přednášky podpořil. A dneska tady máme vzácného hosta, nebo hostku, řekla bych, která přijela až ze Spojených států a je to Regina Barzilay, která je specialistka na AI. A já už bych předala slovo tady kolegovi z Ústavu organické chemie a biochemie Tomáši Pluskalovi, který ji krátce představí. Prosím.
Tak, děkuji za slovo. And I'm going to switch to English now. So it has been my pleasure to collaborate with Professor Barzilay for about 2 years now. I visited her lab in Boston a few times, and actually last summer we were organizing a symposium at IOCB Prague focused on biochemical machine learning. And Regina was one of our distinguished guests, but unfortunately she had to cancel her trip last minute. So it's a very, very great pleasure for me to see her now here, finally in Prague. And Regina is a professor of computer science and artificial intelligence at the MIT CSAIL department and also the MIT Jamil Clinic. And her career started a long time ago, and she was working on problems in natural language processing and built quite a distinguished career in that field. However, at some point, she decided to change her focus, and she's going to tell us more about why that happened. And she is now working more on biochemical and biomedical applications of artificial intelligence and machine learning. And I guess we will hear more about that in her presentation. Her career has been recognized by numerous awards, among them the very prestigious MacArthur Fellowship, and also she is a member of 3 different science academies in the US. So with this, I would like to give the word to Regina to tell us about her work. Please. Thank you.
Thank you. Thank you so much for coming. I've been like 2 days in Prague, and I see there's so many exciting things happening. There was like a concert that I wish I would have gone. So I really appreciate that you decided to come to my talk. So let me just go back and say thank you to 2 people who invited me. So here we have Professor Konvalinka from IOCB that I hope to visit tomorrow, and Veronica Wolf that just introduced me. So thank you very much for bringing me here. So my research today, yes. Okay, so my research today kind of focuses on 2 areas. I design algorithms for clinical AI and for drug discovery. I do molecular modeling for drug discovery. And whatever I will show you, of course, done by many people who are part of my group. I just brought 2 pictures of the group. We are also running every year on 5K in Cambridge. But lots of great ideas that you will see today actually coming from them. And I promised to tell the story of Prague. So this is me in Prague in 2015. And I thought it's really interesting how you guys invited me. It was 9 years. And when I was in Prague, I actually decided to switch from natural language processing and to move to modeling, molecules, doing drug discovery, and working on clinical AI. And the story was the following. So you can see I look quite differently, and it was not a fashion choice. So what happened a year prior to my arrival to Prague in 2014, I was diagnosed with breast cancer. And you can see me in March. It's like my last trip with my son before the diagnosis. I was diagnosed in April. And then in July, when I was doing my chemotherapy, my son was trying to be a barber and cutting, my hair. That's recommended during the chemotherapy that somebody cuts your hair. So it was really a time in 2014 I was treated, and And when I came back to MIT full-time in January 15, I really started thinking that I maybe should be doing something very different with my life. Because, you know, there are lots of people who work on natural language processing, but what I realized when I went through the treatment that actually there is no AI at all in American hospitals. And I was treated in one of the best hospitals in Massachusetts General Hospital. There was nothing. Even the most basic things were not there. So then let's see if it works back. So then in June, you know, I got this very funny curly hair after chemo. And I came with my mom to Prague, and somebody asked me when I was here, they had plenty of free time, like between visiting different locations, including the castle. Somebody asked me, oh, would you want to do machine learning for chemistry? And at the time, this field was really not existing. I said, you know, why not? I don't want to do NLP. I can try other things. And that's how, you know, 9 years later, I'm here to talk about my research on machine learning for biochemistry, which is kind of funny. Okay, so what I want to say, in my talk, I was kind of making comparison between, you know, what machine learning does and how the modern medicine does diagnosis and treatment. And this was my year in discovery when I was a patient in cancer clinic. How do they think about the information that they get? So whenever you're diagnosed with something, you would have a lot of high resolution data. You're going to have your imaging done, you will have pathology. You know, it's like humongous images. Now, what happens next, it's a human who goes to these images, reads them like a story, and it's not even what is used by the doctor. The doctor, they get like a summary. They summarize this image in few categories, and then you're going to get a treatment based on it. So if I'm to make analogy to Amazon, you know, it's like as if we're going to take the whole population and then divide us to 5 groups, and every group is going to get the same product. That's pretty much what's going on today in clinical care. And not surprisingly, you know, when we are looking, let's say those are pathology slides, when we are looking at the pathology slides of women that are characterized the same, they have exactly the same diagnosis, they're going to get the same treatment. Actually, in practice, some of them would be fully cured, some of them would have recurrences, some of them will die from cancer. But we do not see it because we summarize them in such high level, while the original data that we have contains so much information. So since I kind of went through my own treatment, what I decided to do, that I really want to make sure that we are having at least the same level of discrimination as we have when we are doing, you know, our shopping on Amazon. And this is my breast, obviously in the mammographic form. And here what you can see, so I was diagnosed in 2014. This was my cancer, okay? And what you can see that if you go back to 2 images prior, it was already there. And here I kind of blew up the image. You can see that it's actually, you know, it was there, it was diagnosed 2 years later. What I discovered, that apparently a big portion of cancer patients, if you look at the image, like for mammogram, which you take every year, every 2 years, if you look back, it actually was already there. It's just human eye cannot really discriminate. It's not like somebody made a mistake. It's just impossible by human eyes to make this type of discriminations. So what I will do now, I will take like 5 minutes literally and kind of summarize to you how machine learning makes decision. I'm not planning to teach you machine learning because I teach the whole class on it at MIT. But I want to tell to people who never seen AI how machines are doing it, like roughly, so that we can understand the rest of the talk. And for those of you who do know, you can just take your time to read your email. Okay, so let's say in this, I'm going to give like a baby example so that we can really understand it. Let's say you're trying to decide which movies I would like, to recommend me a movie, okay? So one way to do it is to kind of go and ask me which movies I liked and which movies I didn't like. So you can look, let's say, on Netflix, which movies I watched until the end and which movies I stopped in the middle because I didn't like them. So now, if I would ask you, I would give you the pile of these movies with my rankings. You know, you as a human would look at it and say, maybe I like funny movie, maybe I like the movies which have animals in them. You know, you will start having different hypotheses. But it's pretty hard for a human to identify these rules because clearly there are many different factors that come together to help me make this decision, and each one of them may have different significance. So what we will do, we will make kind of this pattern matching. Instead of relying on our intuition, we are going to make it like more systematic. How can we do it? And here people who kind of took statistics would see something very similar. We will take the object, such as a movie, and represent it by this set of questions. We're going to ask some aspects related to the movie. So for instance, we can ask, is it an action movie? And if it is, we will put 1. Is it a comedy? In this case, it's not a comedy, 0. We can ask lots of different type of questions, like features in statistics. Let's say as a human, you have a freedom to decide what they are, but you should be able to extract them mathematically. So if you have IMDb, IMDb gives you a lot of information from the movie, you can translate it into this kind of feature vector representation. This is a correct name. Does it make sense what I'm saying? Great. It's great hearing that you're here. I can ask you questions. Okay, so now what we will do, so we're starting with these very complex objects, which are movies. And now each one of them is going to be represented by this vector, correct? Each one would have its own answers to the questions. And we would also have, my label, whether I like the movie or I didn't like the movie. So this is called in machine learning a training set. You have these answers to the question, you have a label, and what you're trying to do, you're trying to learn a mapping from these vectors to the label. So let me make it even simpler and show it to you at the level of pictures that you saw in middle school. If every movie would have just 2 features, okay? Because I cannot draw in multidimensional space. If every movie would have represented just with 2 features, then each one of them will be a point in 2D space. And depending on the label, whether I like the movie or didn't like the movie, it would have plus or minus. In reality, we're operating in some high-dimensional space, but let's do it in 2D. And then what will happen, we can think that what machine learning model does, it just tries geometrically to separate all the plus examples from all the minus examples. And there are lots and lots of algorithms that do it. So if you are a user of machine learning, you know there are packages, you just give to it this kind of representation, and the package would find you the right separator. And why it doesn't find? Oh, this is the right separator. So now what happens, in this case I show you the simplest separator, it's a linear separator. It's just a line, doesn't have to be so, but let's say you're using a line, and what we would assume is that all the examples on one side of this line are going to be considered positive, and all the examples on another side are going to be considered negative. So how would we characterize a Sherlock Holmes movie? Positive. So if this is correct, so it's going to be on the positive side. So is it clear? So the point is there are 2 pieces. You need to take your objects, be it cell, be it molecule, be it movies, represent them as some feature vectors, and then there will be some machine learning algorithms that can divide them. So it's a very simple story. Now, again, for those of us who still remember middle school math, you can think about it, that what the line does, it actually weighs differently the coordinates, correct? So in this particular case, you can think that what you're trying to do, you're just trying to find how to weigh each one of these factors to give, a weighted sum so that we can make our decision. So whatever you would have done when I ask you, imagine I give you my movie, you would try to guess what I like and what I don't like. So you may say that she really cares about this characteristic, but less cares about another one. That's exactly what machine here does. It just learns these weights. And just because I was talking to you about like a very simple linear separator, some of you are thinking, and what is the big complexity that comes from deep neural networks? So here you can just imagine this is again the same vector, the same features. And here what you're doing, you are taking all these different aspects, learning the weights, and this would be one coordinate, which would give you one way to combine all the input features. And then you can find another combination, and it will be the second one. So what you're pretty much doing through these weights, you're learning how to transform the input vector in a way which make it easier to separate, because you can imagine that the points can be really convoluted and you need to do many transformations to separate them. I just want to say one thing which is kind of essential to our discussion about neural network before we go back to medicine, is to look at this picture. So there is a way when you have a neural network kind of to see what every layer of the neural network identifies, what kind of patterns it learns to identify. And here I'm showing you the patterns which correspond to a neural network that is trained to recognize faces. So it's only trained on faces. It was never explicitly told that the human face has eyes or ears and all the parts. So now let's look what each layer produces. You can see that the very low layer does what our primitive vision does. It just identifies like line and dark and white shapes. Very simple one. The second layer learns how to take these geometric pieces and identify kind of the blocks that correspond to different parts of the face. Again, it's roughly looking like parts of the face. And then the third layer takes them and again learns how to create a face out of it. Why this example is interesting? Because when we are thinking about biochemistry, when we are thinking about medicine, we always ask this question: what is a biomarker? What is a rule? How we explain this rule to the machine? So in this case, what this particular example shows you, that the model that never knew what is valid human face in terms of different subparts of the face was able to learn it automatically. And this is the approach that we will take to medicine and to chemistry, where we will actually make a machine learn directly from the labels. We would never put our knowledge inside the machine. Okay, so let's go back to the breast scenario and see how we can do with the machine things differently than what humans are doing. So what you see here is several images of mammograms, standard mammograms. It's an X-ray of the breast. And if you ask what humans can do today with this image, so the human radiologists, the only thing that they're trained to do is to look at this image as to say, does it have a mass? Does this patient have cancer? So in this particular case, this image does have cancer. What we will try to do is to look at the image that now nobody thinks it has cancer and predict whether this patient is going to develop cancer within up to 5 years. So this is a task that humans cannot do it. Now, for many in the audience who don't care about mammograms, we now can do it on the lungs, which both men and women have, and also on prostate. But I will give you examples on mammograms. Okay? Now, let's think about it. How human doctors are deciding about risk. So the question that we are asking is kind of to predict the future. Clearly, it's not a new AI question. Many doctors thought about it. And maybe the first of them, that I found in the literature, is a guy called John Wolfe. It was an American doctor who is in 60s, before I was born. Asks the same question. He said, I want to look at the image of women who are diagnosed today and see what happened to them 2 years ago. Is there something in their image? He even said to us that he analyzed it by computer, which I cannot even imagine what it meant at the time. But let's say, so what he did, he asked a good question. And then he said, okay, there are different patterns. So women who have a lot of white stuff, which is called dense breast, which means they have a lot of fibrous tissue, those women are likely to develop cancer, and they are likely to have this cancer miss because it's white. So in European and American medicine, women who are in this category, they actually can get extra screening and various things because they are considered to be high risk. And these women who are non-dense, they are considered to be less of a risk. This is pretty much a standard way to decide about the risk. So human identifies some patterns and looks at them and says, who is at risk? Now, it's an interesting question to say, does this feature actually work? How does it work? So, again, a simple way to look at the risk model, people do the same things that we did with movies. You remember I asked you the question, is it like a comedy? Does it have animals in it? So here you can ask a different question about a patient, ask, what is their age and family history and whatever. and try to do a simple statistical model to predict risk. So it turns out these models, which are used today in clinical care in the US and in Europe, they don't work really well. So there is a measure which is called AUC, area under the curve. So for those of you who haven't seen it before, I just would say that if you are perfect, then you are 1. If you are random, you are 0.5. So the model that is currently used in clinics that decides who gets what has an accuracy of 0.6, which is kind of very uncomfortable, very close to random. You say, now I'm going to add this density, how much white is in the image. So you do get some improvement. You move from 60 to 63, but really, and the funniest part, and this is an article that is not written by AI person because they say they rig the data. This is actually written by a radiologist. What they show, that if you show to this group of, I think, 80 radiologists or something, they gave images and asked them to rank the woman who is like dense or not. You can see that some of them found 6% of the women as dense and others found 84%. So it's really like reading tea leaves. Everybody sees different things in the image when they read it. And this is how we decide about the risk. And this is really, really concerning. And furthermore, to make it even worse, in the United States, I'm pretty sure it's close to Europe, it's even maybe higher, 42% of women are considered to be dense. So you're saying to almost half of the female population, you are at risk, which doesn't mean anything. You cannot really do a lot of things if half of your population is considered to be at risk. The last thing that I wanted to say, to make the matters worse, at the years of Trump administration, they made this federally mandated biomarker, which means that every woman who goes today to do mammogram in the United States has to have a letter that say you have high density if she does have it and you are at risk, which is funny, correct? Okay, so what I want to say, that when we took this measurement, which is called density, and these other clinically used things, their prediction accuracy is really terrible. In density, we've seen that it's random. If you're deciding who is going to get cancer based on density, clinically used model 63, the models that we develop with AI gives you a AUC of 77. Of course, it is not perfect because we never know what's going to happen to us in 5 years, but it's already much, much higher. So how you can teach the machine to look at the image which doesn't have cancer and say what's going to happen in 5 years. So what are your thoughts? I know I'm not supposed to ask questions, but how would you approach it? I would let Ian to rest because he already contributed. And I would not ask David because he knows the answer. Anybody? How would you train the machine? Yes?
So you will, I guess you will feed it test data of people who had cancer and their progression of it, and then it's going to be like guessing how the progression is going to work out.
Yeah, so something like that. So what we will do, we will take the images of women, let's say, from 2018. From 2018 until now, we know what happened to these women, and we can take 2018. We know what happened to them until now. Some of these women, when we look at their old images, would not have cancer. Some of them would have cancer in 3 years. Some of them would have in 5 years. So now the machine actually has a label. It has an image, and it knows what happens. And we force it to learn the correlation between the image and the outcome. The same way as your iPhone can recognize your face. If we don't know why, it's because you have certain nose or certain eyes. The same way we're going to take an image and the outcomes and machine forced to learn the correlation between these very subtle features of the image and the occurrence of cancer. And what I want to say is that this model actually works quite well. There are a number of hospitals where it is used. For instance, during the pandemic at MGH, and this is MGH, you couldn't go and get a mammogram if you're not high-risk patient because they wanted to reduce number of people in the hospitals. So using this model, they identifies who are the women who really have to get screened first. And we tested this model in many different locations around the world. This is a published result. And since then, there are many hospitals in very exotic places in the world which actually are using the model in various capacity, or at least retrospectively testing the model. And we are really hoping that this kind of modern tools can be used what am I doing wrong? Can be used to predict future risk of breast cancer. And I just want to say a few minutes about the model that we published last year. and it relates to lung cancer. And again, you know, I got into lung cancer in a very personal note. I mean, I didn't get it, God bless, but the sister of my friend, who was very healthy, she never smoked, she was running, doing all the right things. She was in early 50s. She was coughing for half a year, and then eventually at some point, she got tested, and they discovered that she had lung cancer, and she passed away. And you can see that even the prevalence of lung cancer is relatively low. You can see this is the #1 killer for both men and women. And many of us, including the doctors, have this very incorrect idea in our head that the only people who get lung cancer are smokers. Just before I came to Europe, there was this very big study that came out to UCSF that demonstrated 80% of Asian women who are diagnosed, they never smoked. So there are a lot of, in the US, there are a lot of patients who never smoke and who are getting lung cancer. So SIBL, this is a model that we developed with this doctor at MGH. Her name is Risha Sequest. She was actually a doctor of my friend. That's how we connected. We developed SIBL, and I just want to show you, this is interesting. This is a distribution of lung cancer in the United States. And you can see that it has, we can do the same for Europe and other places. There are very clear patterns where it happens. And last year there was an article in Nature that really gives us a lot of biological understanding related to correlation between exposures and the occurrences of lung cancer. So this whole idea about lung cancer is smoking. Of course, smokers have increased risk. And I just wanted to say that the guidelines today are such that those are all the people that got cancer. Only 40% of them were eligible to get screened in the first place because you need to smoke a lot to be able to screen, and a very small portions of them got screened. So the point is that we really need to have a way to be able to screen and to tell to a person, independently of their smoking status, whether they're likely to develop lung cancer. And because we did the study, we are actually using SIBL operates on low dosage scan CTs, which are very high resolution modality. We can do it even more accurately than we do it on breast. So here you can see an image of a patient who was part of the trial. He was sent home, and they said there is nothing in it. The machine was able to, you kind of can use the attention of the machine to see which region it considers to be suspicious. So doctors didn't see anything on it. And then you can see that within a year or two, this patient developed lung cancer there. So in some way, what it shows to us, that it's not that the machine looks at risk the same way as we think about like genetic risk on BRCA, that even before the, you know, a girl has breast, she has increased risk of breast cancer. In this case, we believe that there is a lot of sign and inflammation and other things, and machines just can spot it better than humans. Now, until now, I was talking to you, this is so amazing. We have all these machines that can predict and do stuff that humans cannot do. And it gives us a lot of hope and enthusiasm. And it's especially exciting because originally, most of the AI models were used to do the tasks that humans can do. But now we're actually moving to the new frontiers, and we're saying that AI should be used to do tasks that humans never even attempted to do. So this is, again, a new setting. While these great things are happening, there is a lot of concerns about utilization AI in the society, and one of the concerns is that AI is actually going to make discrepancies between different people much stronger than before. And we know that, you know, one of the big problems of these AI models, if they are trained on a small data set, not on a very large data set, they don't really perform well. And in this case, you can imagine that your model was trained on one type of population, and then you apply it to different population. Different can be just different hospital across the road, which just treats different people. There is no guarantee that performance is going to be the same. And in fact, there were a lot of studies, not even in medicine, in cell phones, that when Apple brought you know, an ID to your phone, it was unable to, for instance, recognize people with darker faces because they were not part of the training set. And the problem that we all are currently dealing with, that you know, there are a lot of funny things that may be happening in the systems that we don't even know that they happen. So this is the story which is funny, not again where the funny part of the story is that it took several years until the blogger from Huffington Post found out that each time when the actress Anne Hathaway is in the news, Berkshire Hathaway stocks go up. And you can imagine that people who actually are doing it for real, they really care to optimize their algorithm. They were not aware that it was going on. They were not aware that their training data never actually seen, you know, Anne Hathaway, and never seen the name Hathaway is related to the actress. So it was doing this wrong decision. So you can imagine that you have an AI system that does a task that humans cannot do. So you cannot validate what AI model is doing. And it systematically does some really funny things. And again, the shift can be demographics, clinical setting, device, and many others. And there is a lot of hope that if we only be able to make AI explain to us what is it doing, then we are golden. And there are like endless number of doctors that are kind of telling me, Regina, what is it seeing? What this Mirai, which does breast, or Sibyl that does, like, what is it seeing over there? And my point is that if machine does the task that human is doing, then it's fine. The machine can really tell you, you know, you try to identify this calcification. Machine identify that this is a part where calcification happens, you can validate, is it correct or incorrect? But what happens if you are asking machine to do the tasks that you cannot do it yourself, correct? It's like, imagine to yourself that your dog could speak. The dog has many more olfactory receptors that you do. So how it will explain to you how it senses very different senses? And here I just thought that this quotation will be the best in expressing this sentiment that, you know, we really cannot understand the complexity of the patterns because our capacity to recognize very complex patterns, our capacity to remember is much more limited than the capacity of the machine. And what is very scary here, that if you look both on FDA and EMA regulation, they highlight interpretability of AI model as one of the requirements. I am not even sure what exactly it means, to be totally honest. And my colleague at MIT, Professor Marzia Ghassemi, did this study that was published in Lancet. It actually demonstrates that when you give to the doctors false explanation or incorrect explanation, they actually buy them, and it decreases their decision power. So we really need to rethink what do we mean to make this model explainable. And just on the technical note, we spent quite some time, and we have the papers in machine learning conferences, trying to build these meta models that can look at the machine when it makes a decision and identify when it's not confident in its own prediction. Kind of to teach it to say, you know, I don't know, to make the machine abstain. And you can actually do it. You can teach the machine to identify in which part of the space it's kind of very far from what it knows. And we now added it to all our tools, and we can see that it significantly increased accuracy if you give it some budget to abstain and to say, I don't know. But I guess what I'm trying to say, there is really a need. We as humans, with our intuition, cannot really monitor this technology because our capacity is very limited. We need to create another AI, and a very complicated AI that can actually spot out all these abnormalities. So just to summarize, I believe that I just give you some examples, but with everything that's going on in AI, I give you examples related to imaging, but there is also a variety of other modalities. We're changing diagnostic and redefine the disease signature. Now you can, the same way as Amazon is personalizing whatever you are buying, we can personalize treatment in a similar way. And a lot of what we are doing now in the hospital can be actually done at home due to the monitoring. And the final thing is, I don't know about Prague, but in Boston there are MGH and other hospitals. And there is a great doctors here and okay doctors there. So there is a lot of variation. And the hope is that if you're using tools, they can actually control and give theoretically the best quality to everybody. And before I move to pharma application, I just want to show you this slide. It talks about the United States, but if I may, I don't think it's very different in Europe. So every single time I would give a talk or interview, people would say, you know, I say, there is no AI in healthcare. They say, no, how do you know? I said, I go to the doctor, I don't see any AI. And I asked, did you see AI in your care? They would say, no. At any rate, but it wasn't like really scientific, this discussion. So my colleague at Stanford, Professor James Zhu, wrote this paper last year when he analyzed 16 billion codes of the insurances in 5 years in the United States. So whenever you go to the doctor in the US, they would, you know, they give you a pill, there is a billing code. You know, they did you an image, a billing code. So everything that's going on, what's given to you, you can see it based on the billing codes. So he wanted to know in his team how many tools, AI tools that are approved by FDA, that theoretically you should be able to bill for them, are actually billed by the insurers. So they find 500 FDA approved tools, only 16 had a billing code, and only 4 had more than 10,000 bills. 10,000, you know, out of 16 billion. So overall, all the AI tools were less than 100,000 billings. It's nothing, really nothing. So you really can see that AI didn't penetrate in clinical AI, but the good news is that we can see that at least the derivative goes in the right direction, that there is significant increase. So the hope is that, you know, we are going to be seeing the change. It just takes time. I just want to say that, you know, as I already alluded in the talk, there is a lot of confusion in the regulation. FDA, EMA, we're not really clear how to do it. We don't know how to do generative AI regulation. And all these questions are really making very hard to translate this technology into care. But I hope that it's going to change. Okay, so now I want in my remaining, I think, 10 minutes or whatever I'm allowed to do, to talk about AI for drug discovery. And again, this part really started in Prague. Okay, so if you are to look at, you know, how the discovery is done, a lot of aspect of discovery, oh, let's see, oh, I have this beautiful animation, let's see, yeah. So a lot of the discovery happens when you are trying to find a specific molecule with specific characterization, you know, in the humongous set of possibilities, billions of possibilities, and you want to identify the one that does the right thing. Now, since it's very hard analytically to say what is the right molecule, in fact, we cannot do it, what all the pharmaceutical companies are doing, or research institutes, you do a lot of screening. And if you're a big pharmaceutical company, maybe you can screen, you know, few million molecules, but there is no way that you really can screen the whole universe of possibilities. So, and that's where AI comes in, because the hope is that if you can analyze the molecular behavior or maybe propose the designs without actually manufacturing them, then you can, instead of traversing the whole universe of billion possibilities, you can look at a small set and check it in the lab. And as you all know, that there was, you know, AlphaFold 3. There are some advancements that came out of MIT. We did a lot of work on DiffDock. This is a diffusion-based docking, on the generation of new proteins. So there are a lot of super exciting technologies that are coming out. And a lot of questions that we traditionally thought of them as a question for chemists, today can be done with machine learning. So I'm happy to say that when I was in Prague, I was actually writing that proposal, how you can teach the machine to predict the outcome of reactions. For those of you who are not chemists, we are thinking, when we think predict the outcome of reaction, we're thinking what we did in high school, correct? When we are given A plus B and you need to predict C. And we always are thinking that this is very easy task, correct? Because you can do it at school. The problem is that for realistic reactions, you really cannot do it. And we did experiment with MIT professors. They couldn't do it. Most of the reaction, we cannot really predict the outcomes. So machine today can do it with high accuracy better than humans. Machines can take a molecule without ever manufacturing it and identify what will be the properties of this molecule. You can today optimize without ever actually going into the lab, propose a design and generate it the same way as we do fake pictures today. You can kind of generate the designs and then go and validate them in the lab. So all these things literally happened since 2015. And the exciting part now, let me just give you a high-level slide and then more specific slide. The high-level slide is that today you can look at all these different objects, at the small molecules, at proteins, at cell, embed them all in some very big high-dimensional space and using mathematical interaction describe what actually happens there, to identify what are their properties, to understand how they interact and create new objects that interact better. And the example that I want to give you is something in the area of antibiotics. I have the single paper in Cell, which is supposedly a good biology journal for computer scientists. I didn't know what it is before we got the paper there. The specific area relates to antimicrobial resistance. So as you can see here on the statistics, it's really serious. And, you know, it's a very unfortunate situation if you are in a hospital and you have a drug-resistant specimen for which there is no cure. And the bacteria continues to evolve, resistance continues to grow for many different reasons. And unfortunately, many pharmaceutical companies are really not interested to produce antibiotics because it's not economically viable. So we have a serious problem in bringing new antibiotics on the market. So now I want again to separate how you can think about this problem, or how people always thought about this problem from the biological perspective, and how you can do it in a very simplistic machine learning methods that happen to work sometimes. Okay, so people in biology, and there are a lot of people here in the audience from IOCB who are much better qualified than me to talk about it, but what they've done, I mean not people in IOCB, all the biochemists, you kind of look at the bacteria and trying to say, what are the different ways I can kill it? And there are many different ways you can achieve this killing behavior. And then you say, okay, maybe I need to target a particular protein, and then I can have some particular molecule that can achieve this behavior. So we can kind of analytically say, that's how I want to do my killing. And now I need to find a molecule that will do it for me. Okay? So you start with an idea that you want to understand with our human mind how this killing should happen, and then created a perfect tool. You know, the good news is that today, with the machine learning tools that we have, if you want to go this route, you can. There are, this model is called DivDogs that is developed in my lab that enables you, you know, to take the protein that you're interested in and kind of to find which molecule would go there and how they will interact. You can do it. Complex, but you can. Now, I will propose you another approach, which is kind of really naive and agnostic, and it works. So people in chemistry always knew that there are particular functional groups, which has, you know, some parts of the molecule that drive behavior. Like I took this slide from some basic introductory text that actually identified different sub-pieces that, for instance, correlate with antibiotic activity. So what humans did, they always tried to look for this pattern, for these bits and pieces of the molecule that would drive the property. Now you can say, instead of me as a human postulating what are those pieces and bits, we are going to make a machine do it. How can we do it? We can take some set of molecules and actually do the experiment. We're going to take the set of molecules, and let's say for each one of them, we're going to record whether it was killing the bacteria or not. So you have now a 2D graph of the molecule and a number that tells you how much killing actually happened. And in this case, you're not even using 3D information. You don't know anything about the mechanism. You just know did it kill it or it didn't. Again, there are degrees of how much sophisticated you want to do when you are learning. Traditionally, in computational chemistry, people, when they formulated this problem as machine learning, that use what is called molecular signature. They will take this graph and say every coordinate in my vector would correspond to some substructures. We're not going to be even doing that. We are going to train the model to start with the molecule and to automatically learn how to represent it as a vector so that we can do this prediction. And we actually have done it for this antibiotic that I'm going to show you. This is Jonathan Stokes, who is now a professor in McMaster University in Canada. He was a postdoc at MIT. And what he has done, he took 2,500 molecules and screened their activity against E. coli. Now, he was smart in many different ways. And then after he didn't never tell you how smart he was and really had great thoughts, after we had this data set, I'm going back to this slide, if I can. So then you can just train the model to tell for every molecule, new molecules that you've never seen, how likely that it's going to be a killing molecule. Okay? Is it clear? The same ways I kind of explained to you how you can predict which movies you like. Now you're given molecules and the killing property, and you would have a predictor, a deep learning predictor in this case based on graph convolutions, that would tell you how like a new structure that algorithm never seen is going to be antibacterial against E. coli or not. Now, once you have this predictor, what you can do, you can go to a huge set of molecules. In this case, we took 200 million molecules from zinc, and you can just scan them with this predictor to see which molecules which have a strong antibacterial properties. And you can also add another predictor that would say which one of them are also non-toxic, because clearly there are a lot of bacteria, molecules that kill both you and bacteria. This is not the goal. And at the end, he selected just 200 molecules and tested them in the lab. And from them, he found a few very promising candidates. I would show it to you, one of them next. So this is a Cell paper. So this one is called Halicin. It even has its own Wikipedia page. And it works very well against multiple drug-resistant species. We trained it on E. coli, but it happened to work well against C. difficile and A. baumannii. And now I will tell you how smart he was, that he actually managed to make it work, because 2,500 molecules is actually very little. So the first thought that he had was that if you're just going to take like current antibiotics and things that are not antibiotics, what you're going to learn more of the same. You're going to learn kind of a paraphrases on the current antibiotics for which already you have resistance. So you needed kind of to take a set of new ideas of things that you've never seen but can be antibacterial. And we know that cancer drugs, for instance, are antibacterial, or there is like honey is antibacterial. So there are natural products. So what he did, he used, it's called Broad Institute Library, which had a lot of natural products, anti-cancerous and other things, from which the model learned kind of new characteristics of antibacterial molecules. And also when we did this big screening, he removed all the molecules that look similar to the current antibiotics based on tiny motor similarity, which means that he selected molecules that don't look like antibiotics based on what we know, and then he tested them. And just as a point of reference, that at the time, most of the effort went on doing the experimentation to understand the mechanism of action of this halicin, because it had a new mechanism of action. So I hope that right now we actually can do it sort of automatically. But you can also see that one thing that happens here, whenever you are training the model to take a molecule and learn its property, what it does internally, I didn't go into this in great details, but it also learns to map all these structures into some high-dimensional space which have the following features. Molecules with similar properties as a points are going to be close to each other. Okay? Now you can ask yourself a question. Okay, these two I've seen, I know what they are, they're close. But what will happen here? What will happen here? It gives you now an opportunity to go to a new part of the space where you never had any representative and say, now I'm at this point, I can actually generate a new molecule which further optimizes my property. So this brings us to this whole idea of generative AI in molecules, where we start with some molecular, with some existing molecule, we map them into the space where the height, you can think about the height represents how strong it is antibacterial, and then you can go in the space, like you're going into the mountain terrain, go to the one which have the highest property, and then generate a new one. And these disgusting things that you see on the slide is a poor mice that had ABO money. And in this particular case, we came up with a new antibiotic, which is unique in the following way. That not only it kills this ABO money, which is a good thing, because ABO money infection is really bad, but it also keeps intact all the other organisms that you want to keep intact. So they had a particular set of bacteria that are in your gut that you don't want to kill. So now you're creating something to just kill one thing and leaves everything else. These tools, what I'm trying to say, they give you a lot of flexibility on various behaviors. It would be really hard to engineer by hand, but you can do it with these models. And finally here, there is David Sabatini. He's over there. So I just want to illustrate, to give you an example of some things that we are trying to do together. And this is a very interesting idea that came from David, and I'm the one who is kind of thinking how we can do it computationally. But the idea is the following, that any one of you in the audience who takes a drug, doesn't matter what this drug does, this drug not only goes to where it should go, it also goes to many other parts of your body, correct? And to some degree, for small molecules, this is not surprising. Many of them were designed what is called the Lipinski rule of 5, which is one of the ways to ensure that actually they go somewhere, because if you're going to take a molecule that's not going to get to your organ, it doesn't really help. But again, the problem is that since they go everywhere, we cannot many times increase the dosage because it can have really bad side effects. And also you're getting a lot of effects that you didn't really intend to get. So the question is, can we actually look at the molecules and predict exactly to which tissues they go, so that we can create molecules that only go to one type of tissue, but don't go anywhere else? And you can have a lot of different types of data to help you to decide how to create this type of molecules that are very unique and specific. Again, what I'm trying to say is that this is actually one of the David students, but I didn't know at the time that he was post-student, he's now a professor. We already can see how these tools aid in biological discoveries. All these tools that tell you how small molecules react together with some protein enable you, again, in silico to do a lot of tests that do not require you to do them, in the lab. Now, my point is that it's not like you don't need to do the experiments, but you can be just much more effective in terms of experimentation if you combine machine learning and biology together. So just to summarize, generative AI really changes discovery landscape, and I want to say I am involved with many pharmaceutical companies. These technologies are today used in pharma. We can, theoretically now, we have means to personalize drugs to people if we make their discovery and this adaptation much faster. And one of the most exciting ideas, I think, is actually to do preventive drugs, because today I showed you some examples in cancer. There are also new discoveries in neurodegenerative diseases that we can detect who is going to get it way before the symptoms appear, when the disease is much easier to treat. So the hope is that if we combine this early detection and very personalized drug design, we really can do much better for the patients. And I want to finish my talk with the lesson from history, since we're in a historical place. It will not be that old of a lesson, but still. So this is what I learned about electricity. So apparently the first electrical bulb was invented in 1870. In 81, there were already 2 power stations, one in New York and one in London. However, 30 years since the discovery, 95% of the plants were still using steam engine, because the first generation of bringing electricity failed because they tried to use it and configure it the same way as they did with steam engines. So I really hope that we as a community, wherever you are and whatever you do for yourself, we will find a way to make this powerful technology and bring them to healthcare, to discovery, to chemistry and biologists, and we don't need to wait 30 years for that. So thank you very much.
Thank you very much, Regina, for a fantastic presentation. And we are now open to questions from the audience. There is a question over there.
There is a microphone.
Thank you very much for the fascinating talk. So I have a question about the first part of the story where you showed that the program can recognize, the AI can recognize from the earlier picture that this person is going to get cancer. However, we don't know how it can recognize it, yeah, because as you said, the lion is talking a different language. So is it possible to find out which part of the picture is important for it by changing different parts of the picture and checking whether the program can still predict that it can get the cancer?
Absolutely, and actually it's something that is called attention. Attention in a kind of, I'm trying to find a picture with attention here. Sorry, you have to see my talk again. Here. So attention is kind of, you can think about it, it's a heat map that shows to you which part of the image the model looks at. So here it's a classical case. This is actually automatically computed attention, and it looked here. The problem was that when the human looked at it, it didn't tell them anything. They say, okay, fine, I don't see anything. So you see it. Eventually, it's actually where the cancer was growing. It happened to be so. But at the time, when you run this model, at the time, which is at the point 0, the human radiologist cannot validate it. But machine can tell you where it looks at, yes.
Yeah, but can you modify the picture, make a blood vessel smaller or thicker, or to find out what the AI is concentrating on? What does it consider to be the
It's really interesting. It sees here something that we don't know exactly what it is. And remember that the images that we see in medical images, they actually are visualization of the signals. So there are a lot of small, tiny things that we don't really know what they are. Now, attention can be important. Maybe you remember in the talk that when I was showing this Hathaway example and others, there are lots of examples that were already published in the medical literature where funny things happen, where attention can help. There was this big study that came from National Cancer Institute where they trained the machine to identify pneumonia, which is a very simple task, and machine was doing it extremely well. But when they look with attention where actually the model was looking, it wasn't looking at the chest, it was looking at the stump of the hospital, because apparently the way this data was collected, the vast majority, this pneumonia came because, I don't know, from some hospitals had a lot of these pneumonias and others didn't have enough. So it was just using the simplest sign that it can, which is the idea of the hospital, to learn the correlation. To say it more visually, we always do this exercise at MIT in the machine learning course. We ask them to train a model, computer vision model, to discriminate between cows and camels. And the way you do it, you can just go to Google Images, download all the cows, I don't know, some amount of cows and some amount of camels, and then you train the model. And what you would learn from it, because majority of cows are on the green and majority of camels are on the sand, if you now put a cow on the sand, it would call it a camel. So any correlations that it can find, which it makes it easier, because in the training it never seen cows on the sand or camels on the grass, it learned the correlation. So in this particular case, looking where a machine looks at, does it even look at the lung? It's a good, test that was doing it. However, trying to read it, it's pretty tough. And I would give you an example in chemistry. I remember we trained with this predictor's toxicity model. And you can use this attention to tell you which portion of the molecules, actually the one that the model looks at. And we went to Novartis, to chemists, and we say, does it make sense? So in some cases, yeah, I know that this group is likely to result in toxicity, but there were many cases when the model made the right decision, but they say, I don't know. So that's where it's not clear.
Thank you.
There's another question. Okay.
Yes, so another question on the clinical predictive power. So is the literature concerned at all with the fact that the images that it's using for training are not a random sample of images, but that they are governed by a selective process of who actually gets screened? So the question would then be whether the variables or the characteristics which are driving the selection into screening, but are not characteristics that are actually quantified for the training itself, whether those have additional predictive power, which is kind of a similar question of, the fact that honey was also added to the training set or the cancer drugs. That decision of how we define the terrain over which we look for the peaks, the Himalayas. Where does that selection of the training set come from? Is the literature concerned with systematically thinking about that?
Absolutely. This is actually an excellent question, and it emphasizes how important to be representative and to check that you are representative. So I want to start by saying that, the majority of times, whenever you are doing learning until now, it changes, but until now, there is like a big data set and you learn from this data set. So for instance, for CBEL, we use a data set from NLST, it's National Lung Screening Trial for low dosage CT. Data came from 33 hospitals, but every single patient there not only was a smoker, they were like many pack a year, smoker for many, many years. And the natural question that you might ask, these people are very kind of biased to some degree. Can I now take it and apply it to somebody who never been a smoker? So there is no guarantee. There is never a guarantee. But in this case, what we've done with CBEL, we actually tested it in many different populations, and one of population of interest was Taiwan, because Taiwan, due to environmental pollution, very high rate of lung cancer, so both smokers and non-smokers, it's a national screening program. Anybody can go and do a screening. So the data set there has both, smokers and non-smokers, and then we tested, and the model actually performed quite well. But besides giving, empirical validation, we don't have a really great way to deal with it. And the type of data set that you are using really changes your result and generalization. That's why, because we don't have good way to do it, I was sort of advocating we need to have tools, complicated meta AI tools that can actually tell you, you train it on your data set with whatever characteristic and you did maybe your best. Now, if I give you another example, how can you assess whether it is the right domain for you? And it's really an open question. There is no good answer. And if we are looking like the degree of the problem, like you can look at the regulations, people who are tasked to ensure that we are using safe tools, what they say that whenever you are filing for FDA or EMA, you need to say exactly what kind of data set did you use for training. And then, I don't know how, the regulator would look at it and decide, whether it is diverse enough. But there is no really statistical description on what does it mean diverse enough. So I think that this is a machine learning part that needs to be written in the next few years, is much more systematic approach to your question to ensure that, whatever the training is, the question is it safe to apply it to a population with different statistical characteristics?
Very nice talk. I have a question also related to the first part. So what do you think is the main blocker of deploying these techniques in clinical practice? Is it the techniques, we need to work on them more, or we need to collect more data, or is it the legal issues? Why is it?
So this is like a $1 million question, but I would speculate, and you're welcome to speculate later. So this article that I was citing that gives us maybe the most systematic view, I would talk about the US because it's a different story, but I would give you the arguments that he kind of said that I agree with. The first one, again, in the US, everything that happens is driven by reimbursement, how much the insurance would pay to the doctor. So today, whenever you are using AI in clinical practice, the doctor is actually losing money because the way they are reimbursed is based on how much time they spend with the patient. So if AI makes something faster, then it's actually not worth for them to do it because it affects their reimbursement. And now the Congress and the House of Representatives, this is a question, how do you change the reimbursement? This is reason number one. Reason number two, I think there is really a serious disconnect between people who develop technology, like look at Nature Medicine, at Science Translational Medicine, amazing algorithms that really work, that are published. People who are working in the clinic, they have so many serious concerns every day to address. There is no very clear guideline. How do you take the tool, which is not perfect, but still delivers a lot of value, and how do you translate it in a safe way? So this translational science that, happen when people start using genetic tests or when they use new blood biomarker and the other things that happen there, the doctors were really educated. They knew what they're doing, but, the vast majority of practicing MDs and graduating MDs didn't really study AI, so they don't feel that they're comfortable enough to bring the new technology in. So all these factors actually, changing the picture. But the one bright kind of ray of sun that I've seen was ChatGPT. So ChatGPT, again, talking about the US hospital, already made its way in the following way, that when the part that all the doctors hate to do is to write, what you told them, that they write this story. They don't feel like Dostoevsky, so they hate to do it. So now, actually, MGB and Microsoft, they are working together on a tool which helps to create, so it kind of listens to the conversation, creates a summary, and then the doctor just can edit it. So this is kind of the place where people see a lot of value. It's not as regulated in other parts of clinical care, and it really saves the time. So when we already see the benefit of technology in some areas that they can feel, I think that it's kind of open doors to bring other technologies in.
Fantastic talk, thank you very much. It was also very American talk in the sense that it was very optimistic. If Europeans talk about AI, it's always very gloomy. So do you see any risk at all at applying AI? For instance, for me, we are getting out of our jobs in 5 years, as much as I can see. Not to talk about all the pathologists and histologists. So are there any other risks you can define?
So I think, like whenever you're publishing a paper in machine learning, the way you show that you do better is not an absolute number, because your number can be 70. Is 70 good or bad? It depends on how well the best model available does it. So that's how I'm thinking about it. There are some areas where we are doing really poorly. Like, for instance, the screening area. The reason it's so interesting, US spends over $10 billion on doing the screening. Majority of people who are screened don't need to have screening. Women who are high risk, who need to get MRI, don't get MRI. So we're kind of wasting public money, and we're not helping those who need. So this is an area where AI comes in. You can really clearly see the benefit in the long term, both financially and in terms of patient's outcome. On the other hand, there are areas that just work very well, so maybe this shouldn't be the area where you jump in and bring AI, because it will be much harder to demonstrate that you actually improve. The one area of concern that I do have relates to the question that you asked me about the data. There were studies that show that the United States, all the clinical data that used for training the model come from West Coast and East Coast. It doesn't come from the middle of the country. And a lot of these tools that are developed by manufacturers today, by Siemens and others, they're not trained on everybody. So at some point, how do we know that they really work for Czech population or for somebody else? We also have seen another alarming phenomenon with these tools. It actually relates to the tool that is used in clinical practice for determining what is the name? Blood infection. What is the name of this disease? I actually have a slide on it. Let me just, it has a name. Sepsis, yeah. This was an article, sepsis, yeah. So the sepsis tool is used in the US when you go to emergency room. It predicts what is the likelihood that the patient will develop sepsis because you can interfere. And it turns out that these tools were trained on the data from, 2010, 2012. It was working very well. But because of change in standard of care, over time, the stool wasn't retrained. It actually stopped working. And from high 90s, it went to almost random performance, and it was used on the patients. So the point is that there are still a lot of safety concerns that we don't really know how to address, and there are anecdotes that it happened this way or that way, but we don't have a very systematic view as what we have, for instance, on drugs. So I think this is an area of how to regulate them without kind of suffocating the progress is one of the big questions.
Beautiful talk.
Thank you.
So I was wondering, when you show the images of, cancer occurrence over years, this is actually associated with the severe tissue damage. And when you have a tissue damage, it should also reflect it in the blood work. So I was wondering, maybe you can add another level, or maybe you do it already. You can correlate the blood work of, or the urine, or any body fluids that maybe will have some remnants, of this tissue damage. And then I'm sure that if you find something, then doctors will be more, less reluctant to go to check blood or urine.
So this is actually an excellent idea, that clearly, whatever you see on the image is just one modality, the same way as you look at ctDNA or something, you just look at one modality at a time, and the whole idea is to look at all these different modalities, and you can do predictions much better. From the practical terms, why we couldn't do this study, because there is no data set right now, at least publicly available, that look at all these indicators. You could ask me, why didn't they add, genetic like BRCA, which clearly correlates, with the likelihood of getting breast cancer. It turns out that, even at MGH, you don't do genetic panel until you are diagnosed. So there are a lot of people who never, who are not diagnosed, for which you don't collect the information. So it's very much determined of what information you have to train from. Now, your question, which is an extremely valid question, the need have been recognized. So at minimum, my collaborator, not on breast but on lung, she works with one of the blood testing, liquid biopsy diagnostic, to see that the patients who are based on the CT scan high risk, immediately follow up with the blood test and see what's going on. So we'll have results of that at some point. But also ARPA-H, which is this big new funding agency in the United States, has an amazing program, which is called ADAPT, where the idea is, since the patient diagnosis, to collect systematically, all the different modalities of blood and everything that you can only collect, and then use all of those sources to predict the trajectory of cancer development. But this is exactly the case. It doesn't matter how smart is your machine learning, unless you have the right data, you would be unable to answer the right question.
But now at least you can start collecting?
Yeah. So at lung case, we are starting the collection, and we are very excited because VA, we installed it in VA. They do retrospective validation. VA is Veteran Affairs, which is a very big hospital system in the United States, where a lot of veterans have risk of lung cancer. We're also doing actually studies. We're studying a study in Croatia, a similar one. So it's beginning to go, but it's really, as with electricity, takes time. But great idea. Thank you.
Maybe I'd like to ask one question myself. So you mentioned a lot of public money being wasted in healthcare, and we certainly see that in our country too. But I imagine building a machine learning model costs some money, but using the machine learning model for predictions is actually very cheap.
Yeah.
I'm actually surprised to hear that you can build an insurance company for using an AI tool. But do you think this may lead to better accessibility in healthcare?
So I do believe that when these systems are developed, they are going to be actually used and decrease the cost. And if we think one of the pioneers in this space is UK, which have, single pay insurer system. So we already see some tools. You can predict who is likely to be sick, who is going to have a really bad side effect. So it will come. It's just, for whatever reason, it just takes time. The medical system, as Jan said, to ensure that there is no damage, moves very, very slowly.
Okay, so if there are no more questions from the audience, let's thank Professor Barzilai once more for the presentation. And we can continue with further discussion in the next room informally. Thank you very much.